Hello everyone, and thank you for joining us for today's webinar, Securing and Monitoring Serverless Applications in AWS. This webinar delves into best practices for securing, auditing, monitoring, and troubleshooting the AWS serverless ecosystem. It is being presented in partnership with Amazon Web Services, Epsilon, and Aqua Security. And in the spirit of partnership, we have quite the speaking lineup today. Santiago Cardenas, Serverless Partner Technology Lead with Amazon Web Services, is going to kick off our discussion today and walk us through how to leverage AWS's serverless ecosystem and review the offered services for security and monitoring. Following Santiago, we have the perfect segue to the next segment, which will explain how to gain traceability to monitor, troubleshoot, and get alerts across Lambda Functions. This will be presented by Ran Ribbensaft, Espegon's CTO. And finally, we'll hear from Ariel Schuper, Senior Director of Product Management for Aqua's Serverless Solution line, who will explain how you can gain security visibility into Lambda functions starting from their development stage, deployments, and runtime phases using Aqua Security. Without any further ado, Santiago, let's get started.
Welcome everyone to this joint webinar with Aqua and Epsilon. I'd like to take some time to share with all of our viewers a brief insight into modern application development before we dive into serverless application monitoring and security. We'll also explore how the AWS serverless platform can help customers focus on their business logic without servers to manage and operate. Finally, I'll dive deeper into the operational responsibility before handing it off to Ron from Epsilon, who will talk about tracing distributed serverless applications. It's evident that software systems architectures are evolving. We see that every day when we talk to our customers. Monolithic applications try to do everything and are tightly coupled. This leads to fragile software that scales very rigidly and requires over-provisioning to handle increased loads. If you need to release a small change, you may find yourself having to rebuild or recompile the entire application and then run the entire test suite to make sure that there are no regressions. Now, if all tests pass, and then you find yourself having to redeploy the entire app. The evolution normally centers around separating and decoupling the monolith into smaller minimal function services, or microservices, as we like to call them, that focus on one thing, and that one thing they do it very well. Each microservice often has its own data store and can be deployed or scale independently. They represent the real world where service boundaries actually equal business boundaries. This also leads to an evolution of the teams by giving them some of the autonomy to architect, develop, deploy, and maintain each microservice. DevOps principles also fit nicely with automated pipelines and developers owning production support. Cloud-native microservices then take advantage of the cloud for elasticity, platform and software services. Finally, you end up with the ability to make decisions really quickly because decisions only really impact the individual services. After all, innovation requires change. You can learn faster by making lots of little changes to drive incremental innovation rather than waiting to take one big leap. If you're familiar with the AWS cloud, you've likely heard us talk about the shared responsibility. In short, a shared responsibility model implies that there are parts of the system that AWS is responsible for, and there are parts of the systems where you as a customer must take responsibility for. All in all, AWS is responsible for the security of the cloud. Those are things like hardware, software, networking, and the facilities that run AWS cloud services, while the customer is responsible for the security in the cloud. Things like guest operating systems, including updates and security patches, application software monitoring and security, configuration of firewalls, managing your data, and applying the appropriate permissions. Now, when it comes to operational responsibility, it's a spectrum. On one side of the spectrum, you can leverage the power and flexibility of EC2 to run your own database, or use RDS to simplify the management of that database. Alternatively, you can move to a fully managed database like DynamoDB, where you create tables, put data in those tables, and query it on demand, all with no infrastructure to manage. We ask ourselves, how can we continue evolving to further reduce the undifferentiated heavy lifting so that our customers can focus on innovating on business problems? That's exactly where serverless can help. So what is serverless? When we say serverless, we mean it's the removal of the undifferentiated heavy lifting that is server operations. This is an important distinction for customers because it allows customers to focus on building the building of the application rather than the management and scaling of the infrastructure that supports this application. This means not thinking about infrastructure provisioning, operating, patching, or scaling. It also means you only pay for what you value, like consistent throughput or execution duration, rather than server units, and all with high availability and security built in. So many customers think about serverless and Lambda together a lot, but serverless is actually a lot more than Lambda. Compute services can and have been commoditized. Like just look at EC2. AWS led the way with Lambda, but there are other serverless compute services available today. For example, AWS Fargate allows you to run containerized workloads without worrying or having to scale the underlying cluster nodes. While Lambda and Fargate offer many key advantages for our customers, it's really when all of these other components surround them that we start seeing much bigger benefits. Messaging, workflows, storage, and compute together are really the secret sauce. In fact, it's really when all these components come together that we really start seeing, the big gains. So let's dive a little deeper into the two serverless compute options from AWS. First, we have serverless functions in the form of AWS Lambda. Lambda can offer great agility and economic benefits. With Lambda, developers write code in units called functions and define a trigger to run the code. Lambda starts, stops, and scales automatically based on the usage load it receives. For another class of applications, you may want a little bit more control over networking, or how services communicate with each other, or how what your packaging should look like. Here, the unit of work goes from being a piece of code or a function to a set of container images stored in a registry. In this case, you don't want to have to think about how you take that bundle and if the cluster has enough capacity to launch it or what it will look like. You can just define it and deploy it. And this is what Fargate does. Now, to recap a bit on the operational responsibility of various AWS compute services, we start from the bottom and work our way up from less opinionated to more opinionated compute share responsibility. So if we start out with, on EC2, AWS manages the physical infrastructure and facilities, while the customer manages things like source code, integrations, scaling, network configuration, and patching. Now, on containerized workloads running on the Elastic Container Service, the container orchestration responsibility is taken care of by AWS, while the customer focuses on the cluster nodes. If we go one step further, with Fargate, the cluster scaling is managed by AWS and allows you to focus more on your business logic without worrying about the underlying hardware or cluster nodes. Ultimately, now with Lambda, AWS manages all of the provisioning, scaling, and runtime of the application. Lambda also includes integrations with many AWS services and partner offerings. And with that, I'd like to turn it over to Ron, who will tell us more about monitoring serverless applications.
Thank you very much, Santiago, for this enlightening part. Now, in my part, and specifically in monitoring, I would love to dive into distributed tracing in the serverless era. So it's much more crucial to have a better monitoring and troubleshooting for our applications. So I'm Ron, the co-founder and CTO here at Epsilon, and let's get going. The first thing that we would love to notice is, why are we doing that? The need for monitoring is an obvious one and a crucial one. The first one is that we want to understand our application health, to understand what our traffic looks like and how many errors do we get. In serverless, we also need to know about timeouts and out of memories, and also cost. It's something that starts to be an interest for each and every one of us to understand what's our cost impact. Also, we need to know what's our performance. We've got some SLAs that we need to meet them. Do we cross them? Are we close to them? So it's something that we need to understand. And once we're crossing them, we need to know where's the bottleneck. Is it the database? Is it the message queue? Or even our own code? And last but not least, we also need to troubleshoot our application. So once something bad happens, whether it's error or performance or anything else, we need to dive into the logs, we need to dive into the traces, understand exactly what happened, what went wrong, and how can we fix this as quickly as possible. The applications that you've mentioned, Santiago, and it really resonates, it's getting more complex and complex. You're leveraging the cloud infrastructure to have your own API gateway or web servers and message queues like SNS and SQS, and compute like function as a service or Fargate or managed orchestration. And also, third-party APIs like PagerDuty and Twilio and Stripe, things that you don't want to develop on your own. This leads me to the fact that applications becoming more and more distributed, and also in some sort of a way event-driven. So now for a Lambda, for example, you don't need to wait and have a poller that checks a message queue or something similar. You just get an event, hey, there's a new message, react to that, do something. And it makes our life as developers and engineers harder, because now it's not a single monolithic place that we can troubleshoot and monitor everything that happens. It's a more complex way. It's a flow that we need to understand. It's something that goes from one end to another that we need to inspect when something is not working properly. And that's exactly distributed tracing that we're looking for. Distributed tracing tells us a story of a distributed system and a story that propagates through that system. On the right-hand side, we'll be able to see an example with a client and a load balancer, an off-service, billing service, and some other resource where we can see in a visualized way how the request coming from the user as it propagates through different services in my application. And this is just 5 services. It can grow, to hundreds of microservices. The other way to look at it, this screenshot taken from Jaeger, is more of a performance overview. So how long do I spend in each and every of my services and each and every call within that? So if I would tell you, for example, hey, let's improve the performance over here, or let's optimize it, we would know exactly where is our bottlenecks, or what do we need to improve in order to make our customer experience a better flow in our system, in our application. So this is useful for understanding the journey and detecting the bottlenecks where they happen. The best practices for monitoring Lambda functions. So obviously out of the box, you're getting a lot from AWS and it's all under the CloudWatch solution. So starting with the first one, the CloudWatch metrics, where you can get, if you'll switch the tab from the Lambda tab to the monitoring tab, the metrical tab, you'll be able to see average, mean, and max durations, which are good, as you can see an example over here, to understand, is my Lambda working properly? Do I get any spikes, or what happens on my fastest running times? You can also look at the number of invocation, which as a golden signal, it tells us how much traffic do we get. It's a good metric to understand whether we got some spikes in the traffic or downtime or something that is not working properly. And to that, we also got the error rate. So to understand how much errors do we get in our application. And also something that is not listed exactly in here, but the iterator age, which I think for stream-based events like SQS, Kinesis, DynamoDB streams, it's one of the most crucial elements in the monitoring part, because this tells us what is the age of the latest record that was being processed. So if we're having any kind of bottleneck or any issue with parsing time, this will tell us, hey, you're falling behind for an hour or a day, and you're not up to date with the new information. We also got CloudWatch alerts, because obviously as a good engineer, you don't want to wait in front of the dashboard all day. And with CloudWatch alerts, you can set up any alerts based on what we saw so far, but you can also set up custom thresholds. For example, let's say if I'm getting more than amount of errors or a percentage of errors, I want to get notified. Or if I'm getting less than amount of invocations, I know that something is not working properly. So even custom thresholds are configurable through CloudWatch alerts. You have to bear in mind that for every Lambda function that you have, you need to take out all these metrics and configure all these alerts manually, but that's a good starting point. In troubleshooting, so we talked about the fact that we need to understand that the system is working properly now. When something bad happens, we need to understand what went wrong. And logs are probably the go-to place for every engineer. So out of the box, Lambda streams out all logs to CloudWatch logs. So every print or console write that you'll make will get out to CloudWatch logs. Many people like the experience of Elasticsearch service with Kibana for searching and creating some more dashboards. So AWS already gives that built-in integration to stream out all information from CloudWatch to Elasticsearch, their own managed Elasticsearch, so you don't need to manage your own. But you can also stream it to a Lambda function for custom handling. So for example, if you want to stream it out to a different service or to some external API or to PagerDuty or to something that is meaningful for you that you want to get these alerts or this parsing for yourself, you can do this with an easy integration straight from CloudWatch log to your Lambda function. So that's really easy. Now let's talk about some more advanced scenarios. So in this example, I've got a scenario of a shop e-commerce website that is leveraging most of the AWS services like CloudFront and S3 and API Gateway and Lambda function and some external resources. And as you can see, it's pretty distributed. I mean, and it's not even that complex. It's just a simple distributed application. And on top of everything that I've mentioned, some things that we need to bear in mind when we're monitoring such distributed application is, first of all, the overall application health. So, it's not just the Lambda function error rate, is also what about the API gateway and the DynamoDB and the KMS or the SNS and Stripe calls. All these resources are something that we need to bear in mind. Now, also, we saw that CloudWatch metrics gives us average, mean, and max durations, but percentiles are the one that are crucial to monitor. If you want to meet your SLA, for example, the 99th percentile will be lower than a second. So you want to look also at percentiles and understand how they distributed over the 100 percentiles that you got. There are also some specific scenarios for Lambda functions like timeout or out of memory. And here I want to stop for a moment and talk about it because when you set up a Lambda function, you have a limited amount of time that you can configure for yourself to run or memory to get consumed. So if you're not aligned with what you configured, you might get this issue of a timeout or out of memory because you haven't configured it right. And if you're not having a look at what's your current consumption of both of these, you might end up with a broken application, which leads to errors, which leads to angry customers, and none of us like them. And also, when we're talking about errors, it's not just about, okay, how many errors do I get, but what are the type of errors? Is it a critical error? Is it just a small exception? Do I handle it correctly or not? So even understanding the specific errors is crucial. Now, correlation between logs. If we see that one of our Lambda is performing slow or some requests that are coming through the API gateway is performing slow, I want to be able to correlate between these and the logs to understand what really happened inside of it, and honestly see also traces which contain some more payload information, some more data. And also just in general, being able to understand this kind of visualization and understand how my system is flowing from one end to another, that's super crucial today. It's getting more and more complex, and if you don't understand how your system operates in production, you'll be having a hard time to iterate faster and troubleshoot problems in production. That's exactly where Epsilon comes, and with the state of mind that everything should be managed for you and you should have the best experience as an engineer to get a solution out of the box, Epsilon comes. Out of the box, it discovers all Lambda functions and show and reveal performance stats, including everything that we mentioned, percentiles, timeouts, out of memories, cost, and so on. It also automatically traces any kind of application, whether it's a Lambda function or Fargate, and it talks to AWS SDK resources or HTTP calls or Redis and Mongo and Kafka. All these resources will be listed automatically for you. You'll be able to search and visualize payloads at any data or any payload that you've ever imagined that's going into your system. And as I mentioned, it's completely managed, so you don't need to set up anything on your own. And I think it's worth spending a minute or two just to show the capabilities of Epsilon. So let me jump quickly to the demo. This is our demo environment at demo.epsagon.com. You can reach it at any time just to play with it for yourself. So the first thing is that Epsagon explores and enumerates your account with all of your functions and all of the ECS and Fargate clusters. I'm going to focus specifically on the serverless part in here. And then you can see all of the functions from multiple AWS accounts from any region and any runtime. You can see how many traffic and invocation does it get, how many errors, but not just errors, also breaking down to timeouts and out of memories, as you can see that we're getting them. Last invocation, average duration, and estimated monthly cost based on the selected period. So again, cost is becoming a matter of understanding what's going in my application. Jumping quickly to the specific function that I'm having here. So it's a blog site prod post analysis. I'd be able to see a breakdown for every invocation and error over time, the memory usage and duration. Please note that everything is presented in percentile. So I know that by the average, I'm running less than 50 milliseconds, but I'm getting some spikes from some of my users that, they're not having the best experience as I want, which is less than 100 milliseconds per request. I'll be able also to scroll down and see each and every invocation that happened in my system. So once the function is being invoked, you'll see that here, the request ID, the resources, time it happened, duration, used memory, and status. And everything is filterable, so it's very easy and convenient to say, show me only exceptions or timeouts, or show me only invocations that took more than 100 milliseconds, or even looking for a specific request ID is very easy with Epsagon. And as we know, the second part that we're looking for is, okay, show me what are the logs of a specific invocation. We can see that we're getting here some sort of a recurring problem. So jumping to the logs is very easy. Using the Epsagon integration, you can click on CloudWatch logs and get the exact logs from start to end, including the report line, where I can see the traceback. But sometimes logs are not enough. We're looking for traces, or we're looking to understand what was the flow that led me to this problem. So I'll be able to click at any kind of invocation here, and I will get a trace view. A trace view composed with all of the resources that led me to the point of the post analysis being breaking down. And again, I can see the error, I can see everything that happened, I can see all the retry attempts that we had over here because it failed on a stream-based event from an SNS. Now, the second thing that I would love to do is to see, okay, what was the trigger and what was the payload of that specific trigger? So I can click on the SNS and within that see the actual metadata, but also the payload itself, the notification message. So I know it's a Netflix event with the title and the JSON and everything that came over here. Then since Epsagon is doing distributed tracing, I can go even backwards and see like, okay, what was the Lambda that published that message to this SNS? And I can see that exactly and correlate the logs and see the return value and see also for the API gateway, what was the headers and the response body and the request body. And also any call to any other SDK like HTTP calls, Redis, Kafka, and other things like that. I'll be able to click. In this example, it's an HTTP call to auth0, which takes a lot of time. And in this example, I can see why. I can see the response body or why did I got this unauthorized response code. I can see the response body and understand that my JWT was expired in this scenario. So initially, the problem started over here, but it propagated to a different service for a different team. Jumping quickly to the search, so Epsilon gives you the ability to search at any kind of payload, any kind of data, even free text, like let's search for Netflix. We saw that previously we had something in the payload with the word Netflix. So I can see all calls that had within them the Netflix keyword, and I'll be able to click on any kind of them. This kind is an API gateway, and I'll be able to see the full request that led me to this point. So in this example, it's even more complex. I'm not going to go through that, but I can see that, okay, in the response body, probably, yeah, the word Netflix appeared. And also in the timeline itself, I'll be able to see a breakdown of each and every call and how long it takes in my distributed system. So I know exactly where my time is being spent on this kind of flow. Jumping quickly through the architecture. So sometimes you just want to visualize your architecture, all your calls, all your resources. So with that, Epsagon automatically generates it for you. You can see exactly how many errors do you get on, let's say, auth0, or how slow is my Lambda performing. So everything is visualized, very easy for us to understand and see what's going on. And last but not least, as we mentioned, you want to get this kind of alerts to your Slack, to your PagerDuty, to your OpsGenie tools. So Epsilon gives you the ability to ship all alerts and even customize the alerts, like sum of errors is larger than 530 minutes. So I don't want to get each and every error for this specific function, but I want to get a more tailored one customized for me. So that was the demo, and I think we're good to go with the second part, which is security. So I'm handing it over to you, Ariel. Thank you, guys.
Thank you, Ron, for your part on distributed tracing of serverless functions. And let's talk about the security aspect. How do we secure serverless function? So before we start talking about security, let's talk about the risk. What are the risks that serverless function has? So if we talk about serverless and AWS Lambda more particularly, then the main threats or the main risks stem from the code. The biggest threats come from the code, vulnerabilities, sensitive data which is left exposed, and any type of dependency, vulnerable dependency that you include in your software, or any flaws in the code like that allow other different manipulations, whether it's injecting, manipulating inputs or outputs, or anything which related for bad code practices. And another vector or another risk stem from the cloud infrastructure. If you didn't configure your YAML roles correctly, if you didn't track your functions activity, if you left things open, were not secure. I mean, so all of those small misconfigurations which relate to the cloud services create potential threat for serverless functions. If you want to be more particularly, there's an interesting work which was done by the OWASP, converting their top 10 web application vulnerabilities into the serverless space. Create a very nice paper. You can download it from the OWASP website, where they really took all the top 10 vulnerabilities and checked their applicability for serverless function, mapping the top 10 risks of serverless function. So you can see risks like injection, where people inject either code into your function to manipulate the way the function behaves. That you can inject code as an input, which can exfiltrate data from your databases. If broken authentication were not defined correctly, if you left sensitive data as a plain text in your environment, and an attacker can access it and can get it. For example, if you keep your secrets as environment variables, which can be exposed by an attacker by if you don't do proper input validation to your functions, which I'll give you a quick demo at the end of my session. All of those typical risks that we find in applications are well applicable for serverless functions. And I'm not going to go through the entire list, but we definitely can see there's many potential risks. And if you want to map them down, you can see that they can either come from your code, things that you didn't code correctly. If you don't validate your inputs, your outputs, if you leave data exposed as plain text, if you're using a serialized object, which can be serialized by an attacker, and manipulate those objects. Those are things that you are under your control. There's some other risks which are more under the cloud control. Just need to configure, do your work properly, but then you need to trust the cloud vendor to support it, whether it's the authentication, the access control, the logging, the monitoring. All that area is the cloud vendor provide you good infrastructure. You just need how to use it. So in my talk, I'm going to focus more on the left side on how do we protect Lambda users from bad code habits or potential risks that might happen in the code. And when you're talking about serverless security, you cannot ignore the performance challenge. Security controls can impact your function performance. There are some classical control that add significant performance penalty, like for example, encryption. You want to encrypt the outputs of your function. You want to encrypt the communication of your functions. So creating a secure channel, generating a key, encrypting traffic, especially when function starts in a cold start, this is something which can extend the duration, can be painful when it comes to performance. input validation, when you want to validate any input, and there are many input types, and run it through any type of libraries that contain different regex that contain potential attacks. This is again something which has to be done in a very delicate way in order not to impact your functional performance. And again, outbound network inspection is something that has to be taken care of, and many other consideration or many controls that you might be using in a classical environment. You need to rethink about them, whether they really make sense when you want to protect your function. But the good thing about it is if you bound things correctly, you can do a lot of the things offline. A lot of things you can do while the functions are running. You can shift much of the protection or the security inspection to the time that the function is idle and not performing. You can scan the function code to find any vulnerabilities in the code, vulnerabilities in dependencies. You can check if the function code contain exposed sensitive data. You can check the privileges, the YAML roles, if they were defined correctly. You can do all of that when the function is offline, is not running. You can verify the code integrity, that no one manipulated, changed your code in an unauthorized manner, also while the function is running. And if you make all those tests, then you can reduce significantly the potential attacks without any touch or without any impact on the function code. There are some things that has to be done when the function is running. There are critical risks that you need to be addressed when the function is in runtime. For example, injection attacks, that someone is trying to inject code or pass or manipulate inputs, malicious input into your function. This is something which has to be done while the function is running. If you want to verify the serialization or prevent serialization attack, this has to be done when the function is running. But a lot of the heavy lifting can be done while the function is in offline, and by doing it, you can really increase significantly the performance. I would say, you can do a very high level of security without any performance sacrifice of your function invocation time. And let's see some examples and see what we can do in real time. In Aqua, for example, we do a lot of the scans when you start running your functions in your pipelines. This is an example. I'll show you in a minute a live example, but this is an example, for example, of a Jenkins pipeline. You can see in my screen, I took a picture, and you can do the scan as part of your pipeline, and then we can start scan your code. When you finish your code, when you clone it, you pass to us the library that the code exists. We scan the code, we verify there are no vulnerabilities, or if there are vulnerabilities, we can let you know immediately where they are, what the thing that you need to replace. We can also check if there are sensitive data, if you left some secrets like AWS access details, access key, secret key, or any session token which you leave exposed as a plain text as an environment variable in your as an environment of your code, and we'll verify, let you where the things exist and where you need to fix. We also can do it for your permissions file. If you're going to give us your configuration files, we'll scan your permissions, we'll verify that they are done in a least privileged way. There are no wildcards like star. There's no overly permissive resources or actions which you define, and we can help you, guide you to get in the minimal way. So by scanning in the pipeline, you can verify that thing which goes into production are only functions which has minimal attack surface. On the next phase is daily scan of your cloud accounts. We can connect your account. We can verify that all the functions which run on the account that don't have vulnerabilities. Now you can ask me, why would they have vulnerabilities if we already passed it in the CI/CD phase? Because sometimes, there are new vulnerabilities which are discovered. Could be that your function, when they passed the CI/CD, they were perfectly fine, but there was a vulnerability which was discovered recently while the function is already deployed to the cloud, and you want to know about it. We can also make sure that no one by mistake, when you deploy your function, added some sensitive data. We can verify that any code change, any change to the function code or configuration was done by people which are authorized to do so. and any change was done is an authorized change, past the proper channels, and only allow those kind of changes. Don't allow any changes out of the wild, like adding unknown layer or unknown configuration to your functions. And then, last but not least, we can verify that your permissions are really tightly coupled with what your function do. Because many times developers, when they create permissions or create roles, they define, future thinking about what they maybe use or what they want to use, but eventually they don't use it at the end. When we scan your cloud account, we use the AWS Access Advisor API to verify that those services which exist in your permission are services which you're actually using. If we're going to find services which were not used or never used or we're not used in a long period of time, we'll let you know about it. Maybe there are some changes that justify removing those functions or removing those roles from the function. And then we leave only the critical things to the runtime part. And this is something that we do in order to avoid heavy performance impact or anything which can let you feel uncomfortable with the function permissions. And by doing so, we verify that you are secure, you're fully secure, and your performance are great, developers are happy, your users are happy. So what do we do in the runtime? The risks that we're trying to address in runtime are those which are relevant only for the runtime, like validating functions input that they have no SQL and no SQL injection patterns. We make sure that no one running arbitrary code in your functions. We block any malicious executables, any attempt to invoke or create a child process in your function to run something which is not part of the function through /temp. We verify that only the allowed processes are executed by the function. We prevent manipulating the cloud vendor SDK. We check, monitor what you do, and verify that you don't do something else. And we add some cool things into your environment, something which can only be done when you're working in a cloud environment. In a cloud environment, it's easy to create a virtual environment, something that allows us to install honeypots or tripwires, things which can lure an attacker to use them. Because attackers in function has a short period of time. This is something which is derived from the function explicit invocation time, or the time that the maximum time the function can run. And in this short period of time, the attackers need to look for a low-hanging fruit. So by spreading around some honeypots, tripwire, things that can be very tempting to an attacker, we can use virtual environment that has no meaning. But if someone is using it, we know it's a very clear indication that there is an attacker in the account, because there is no other reason why the function would call or use those services or this account. So this thing which is very easy to do in the cloud and can give you a very high level of security without any performance penalty or any impact on your performance. And let's make a quick look at the demo that I prepared for these purposes. So first, let's perhaps start with the CI/CD. So this is an example which I showed before. This is a classical pipeline. Yeah, the Aqua scanner is part of a pipeline before the test. So you clone your code. And when you build, when you're going to build any build in the past, it goes through the scanning. I showed you an example of a scan. You can see it before. This is a function that has vulnerabilities. You want your developers to get this information right on the spot when they are with it. It'll be much easier and shorter time to fix it. This is the case someone left some access key and secret key exposed for some reason in different libraries. And we can also check if you have some excessive permissions in this part. In this case, there is no excessive permission and everything worked perfectly fine. The next stage will be going into your cloud account. In Aqua, we allow you to define an assurance policy. This is something which lets you check one thing that you don't want to see in your functions. And we define the assurance policy. We'll scan your account on a daily basis. And for example, you can find over here a function which does not comply with the assurance. Why didn't it comply? Because it has high vulnerabilities, right? In this case, you can see over here, it has critical vulnerabilities, 8 critical vulnerabilities that you might don't want it to allow it in your functions. So you can click over here, get information about the different vulnerabilities, what are the CVEs, what are the resource which impact, then you can get more details of those resources and know if there is a fixed version, what can be done. And this can give you a very good information on things which you maybe not have been aware of while the function was passing the CI/CD pipeline. Another thing that we do is looking at your permissions. And for example, you can see over here, services which were never used by the function. If those services were never used, might be a good idea to remove them. So by guiding or passing, reviewing your functions on a daily basis, we can verify that only authorized changes were made, no new vulnerabilities were discovered, your permissions are more tightly defined, and again, that everything is under control. The next phase will be to protect your runtime. And for this purpose, what we do in Aqua, we allow you to define, allow you to create your own layer. You create your runtime policy, you create an enforcer. In this case, I created this enforcer in advance. This is a layer. You can download it over here, go to your AWS account, as you can see over here. And when you go into your AWS account, you create a layer. I already defined it to save some time. We call it the Aqua Nano Enforcer. And the Aqua Nano Enforcer provides you a runtime protection to your functions. So I'm just going to copy this ARN. I'm going to use it in a minute. But before we do it, let's show you a quick example. So I want to show a quick example called the OWASP Serverless Goat. The OWASP Serverless Goat is an application, is a deliberately insecure, realistic AWS Lambda services, which is created and maintained by the OWASP, and it follows the top 10 security. In this case, it's an application that when you press on it, it will give you a content of a document. So if you give it the URL of a document, it will convert it to HTML and will show you the content without opening the document. Now, since it's deliberately insecure Lambda serverless, so let's try to fool this function. So if, for example, I'll do cat, I'll do this, I'll try to manipulate it and add some input, which can give me some more information about the function. I'll press submit. Now I can get all the function code. If I'll take all the code, I'll copy it into my IDE and I'll sort it out. I'll find out what's the flow of the function. I'll get a good idea of the flow. In this case, I can see that the function is asking for information which is in environment variables. So in that case, what I'll do is I'll now try to get some environment variables. So I'll do this foobar. Okay, let's get the environment variables of the functions. So now, if everything goes well, what happens is I'll start getting the environment variables of the function. Okay, so give it a minute. And by that, what I can do in this example, I can see their access key, their secret key, and any other environment variable which is left unsecure. You see, we have some challenges here. Let me check again. Okay. Why the problem is, all right. Let's get stuck for some reason, so I'll stop it. And, all right. Force reload. All right, perfect. Great. So now I get all the environment of the variable of the function. So you can see the session token. You can see the access key. This is the access key for AWS. So this is the secret key. Here is the access key. So you really get information which allow me now to get all those access information and now penetrate the account and take over the account and to get any permission the function does. So for that purpose, in order to make it simple and easy, in Aqua, we created the layer, the nano-enforcer layer that I'll show you in a minute. So if I'm going to add this layer now to the function, okay. I'll add this layer to the function. I'll press save. Great. Now I need to add just one environment variable. And this one is, wait a second, let me just glorify it. It's, yeah, node options and -, require. Perfect. Yep. -, require. I'll save it. Check again. That's it, right? Yeah. Perfect. Now, if I try to manipulate my function just like I did before, right? And let's see, for example, I'll try again this cat exercise. Let me see. And I get internal error, okay, or an access, going to be an access denied. Just test the function, verify that it works. Go back again, press it, and you get that you can see that the command failed. We'll try again. We'll try list the env part. Okay, and let me try to see, copy the same exact. It's foobar and we identical. I'll press it again, and again you can see that permission denied, and this is something that we prevent you from doing. So, as I said again, while minimizing the runtime to only those things which must be done in the runtime, like code execution, input validation, we can verify that the performance impact is really minimal. There's no really the users don't feel it, developers not going to complain about it. And we shift all the heavy lifting of the security scanning to those offline parts where no one really impacted and can do it without any impact on the functional performance. So by combining those static scans and the runtime protection, you can give you a maximum protection to our users while maintaining their performance and their ability to use the service and benefit from the serverless environment in a very secure way. So that's about it. This is my part about securing serverless function. I hope you enjoyed the webinar. Thank you, Ron, and thank you, Santiago, for your